did all this setup, and we talked about all these kind of wacky things, what's the whole point of these hypergeometric functions? Well, it turns out that hypergeometric functions are very general. I mean, this is a very general definition. If we have any series at all where subsequent ratios of coefficients is a rational function, that just represents a lot of things. So, they have this example right here, the exponential function. We have 1 plus 1 over 1 factorial plus 1 over 2 factorial and so on. So b of n plus 1 would be 1 over n plus 1 factorial divided by the beta n term, which is 1 over n factorial. So beta n plus 1 over beta n would be n plus 1 factorial in the denominator over n factorial in the numerator, because you have to flip it. And so the n plus 1 factorial and n factorial cancel out in the first n terms, and so we get 1 over n plus 1. Well, this is a rational function. The numerator is just a constant function. Our a of n here is a constant function, which is just 1, and our b of n is a constant function, which is, or sorry, not a constant function, it's just a monomial, which is n plus 1, as it says here. So exponential function, one of the most important functions, can be represented as a hypergeometric function. Lots and lots and lots and lots of things can be represented as such. Here are some examples that they're talking about: the dilogarithm, Hahn polynomials and Wilson polynomials, even more things if we get down somewhere. In fact, if we go back to the basic hypergeometric function, which is just a specific 2f1 case, if we go down and try to find it, whatever. I'm not going to try to look for a table of them. Anyway, things like trig functions, square roots, blah blah blah, can all be represented as such. There are all these neat properties. If you look at hypergeometric functions themselves, you can get all these interesting transformation properties. So if you have one hypergeometric function, you can transform it into another hypergeometric function using all these different rules. And as an example of a rule, we have, for example, these differentiation rules. We can differentiate hypergeometric functions formally. We can use all these transformation rules and so on. So anyway, it creates hypergeometric functions in and of themselves. We can look at them in an analytical sense as a series and do all the interesting things with them. We can do analytic continuation to make their convergence, very large area. We can do all these things, but we can also look at them algebraically in terms of p tuples and q tuples of their parameters. And we can look at transformations between them and formally differentiate them and so on. So yeah, here's one interesting thing, Dougal's formula, which says this 7f6 hypergeometric function, whose parameters are general parameters such that it satisfies this constraint, reduces down to this simple little ratio. Anyway, as you might guess, one particular aspect of hypergeometric functions is that we can represent pi with it. If I look up Chodnovsky's formula, we can look here, and this is the formula right here. Now you have to do, and it says it's a generalized hypergeometric series. So it's not completely evident in this form that's a hypergeometric series necessarily, because we have this square root thing right here, this power of 1/2, and that implies that it's not really a rational function, because that would produce irrational results. We have, the sum term, we have all this stuff, but you can massage this in such a way that we factor out certain things, and this 12 can go to the other side, for example. We can take this 640,320 to the power of 3, actually it's the power of 3 halves, and we can factor that out. And then once you do all these factorizations, we can get this to be just a ratio of this -1, some factorials, this this binomial, and then more factorials and powers of factorials at the bottom. And so you can kind of see, since factorials are a very multiplicative thing, and since powers are a very multiplicative thing, when you divide them, a lot of times they'll divide out, and you're left with a rational function. So Chodnovsky's formula, or Chodnovsky's algorithm, is an algorithm for that is represented by a hypergeometric series, and it computes pi, or at least computes 1 divided by pi. So what I want to code then is something that can, if I can find it back, is something where I can specify the structure of a PFQ hypergeometric function, and I can compute it to very, very, very high precision for arbitrary arguments and so on. That's the ideal. And if I can do that, then I can, in a sense, substitute or plug in the particular coefficients for the Chodnovsky algorithm and compute pi in a distributed fashion. But you can also do a bunch of other stuff. We can compute like Euler's constant, I think, or Apéry's constant, a bunch of different things. I don't think Euler's constant can be computed. I don't remember. So I guess we can start getting to coding. Now, fortunately, I've done some things with this problem before. There are two big things that I've written so far. I've written a small little kind of hacky code for number theoretic transforms, and I've written some code for actually computing hypergeometric functions using a method called binary splitting. So I've written that code before, but it's kind of, it's prototype code and just sort of for fun, but we would need to massage it and so on, and maybe change the abstractions a bit to make it appropriate for this library, which I'm calling Hypergeometrica, which is kind of a dumb name. It is not paying homage to Mathematica in any way at all. It's just I don't know, I just made it up. So the first thing I'm going to do is copy from my Lisp random project, which you can go and visit here. My Lisp random. Lisp random has a bunch of really just random things, anything from FFTs to neural networks to rationalization of floating point numbers to just a bunch of things. A lot of these things turned into projects in and of themselves. But anyway, in here I have, if I can find it, let's see, number theoretic transform. I wrote this code here to do, well, number theoretic transforms. I'll explain what that means in a second. But I want to copy it over, so I'm going to copy number theoretic transform.lisp over to here as ntt.lisp. I will need that the bit reversal code, so I'm going to copy the Lisp random, let's see, the strand Elster reversal code to, I'm just going to call it, I'll call it bit reversal. Just bit reverse.lisp, why not? And then I also want to copy over, if I have it, I don't know if I do, let's see, bin split. And I'm going to call it bin split.lisp. So this is code I've written. I'm going to step through the code a little bit so we know what we have on the table. So I have all these things. I'm going to look at it in, I'll look at it in Emacs. So first let's look at kind of the simplest-ish of them, which is the binary splitting stuff. So binary splitting is a method for computing hypergeometric functions in a very rapid way. If I look up binary splitting on Wikipedia again, the idea is that we have a sum ranging from A to B, where our index of summation goes from A to B, and we're summing some ratio P sub n over Q sub n, where P and Q are defined in some way. So if we want to sum an entire series, we'd sum from A equals 0 to B equals infinity, or B to be some sufficiently large number. So binary splitting, I don't really want to go over all the details of it. There's a very good paper written by Bruno here. If you look in this paper, they talk about how the method is implemented and so on. The idea is that we can compute subsums, as I just described, that S of A to B. We can compute several subsums, and then there's a clever way to combine them without incurring lots and lots of overhead. So they even have a little bit of a sample implementation here. And they actually give some really good examples. The most basic example is computing factorial by binary splitting. There are better ways to compute factorial, but it's a good example. Computing exponential function, as we talked about earlier. Computing logarithm, computing sine, cosine, arctangent, I guess. Sinh, cosh, whatever you want to call them. Anyway, and then of course an example to compute pi. And they talk about how to turn this into a hypergeometric function. Okay, so basically what I have then is coded that. I have a representation of a series amenable to binary splitting, which requires 4 functions. Requires an A function, which is a map between integers to integers, which I'm representing by this z to z. A, B, P, and Q. The computations of our binary splitting are represented by this quadruple here, which take P, Q, B, and R. And the idea is that we can take 2 of these bin split computations and combine them together, which you can see. Let's see. Yeah, combined computations. We have a computation to the left, so to speak, a computation to the right, and using some clever things that are discussed in this paper, we can create a new computation right here that combines them. And in the end, what we get is, so this is the main entry point, compute series, which takes this bin split series function, structure, which represents functionally how to compute the series. So you give it that, and let me go back down to it. You give it a lower bound, which by default is 0, an upper bound, which is by default 1,000, and it computes that series by binary splitting. Binary splitting is going to do basically divide and conquer, that we binary split half them lower to m, where m is the middle right here, and then m to the upper bound. So we get a left and right. Once we compute that, that's going to create a whole tree of computations. Then we move back up the tree and combine everything together. Once we get to the base case, we do binary split base case equals 1. You might be able to guess what that is. It's actually just a trivial call to compute each of the functions within the series. So this is equivalent to summing one single element. And then obviously this is equivalent ideally to summing the general case by doing direct series summation. So anyway, binary splitting, this is kind of the high-level code to do that. I can show a little demo of it real quick. If I start my Lisp up, let's see. So let's load this code. 2 errors. What was it?